We already have some idea about the meaning of sequence of a set of sequence of real numbers. We have seen that sequence is nothing but a function on the set of positive integers, and we also have some idea about what is the meaning of convergence of a sequence, or whether a sequence is convergent, or when can we say that a sequence is convergent or not. We have seen some examples of sequences of different nature, like convergent sequence, divergent sequence, or sometimes oscillatory sequence we should say. So today we will describe first one particular type of sequence which is known as Cauchy sequence, and we can define convergence in terms of Cauchy sequence. Sometimes it is easy to evaluate this, evaluate the property whether a sequence is convergent or not in terms of Cauchy sequences. So we will see later. Also at the same time, we will define another sequence today which is known as monotonic sequence. That means what is the behavior, what is the meaning of monotonic sequence, and how convergence property is related to this monotonic sequence. We will also see some very few interesting sequences, maybe few special sequences and their convergences. We have already learned a few ideas, definitions of a sequence. So now we will discuss few more results, and this is sequence 2. So the objectives are, here we will define one special type of sequence which we call Cauchy sequence. I will just give the formal definition and the idea of these Cauchy sequences. Then another particular type of sequence which we call monotonic sequences. We will again give the definition and results of this, and a few important sequences. We will see the nature of convergence or divergence with respect to these sequences. So first, the Cauchy sequence. The definition goes like this. A sequence an in a metric space X is said to be a Cauchy sequence if for every epsilon greater than 0, that means epsilon is a pre-assigned positive quantity, there exists an integer n0 such that modulus of an minus am less than epsilon whenever n greater than n0 and m greater than n0. This means, in simple language, first consider a large number n0 and consider two other large numbers, both are larger than n0. And consider the sequences, the sequential values at those large numbers like an and am. And if the difference of these two numbers an and am in modulus, in absolute value, is less than epsilon, we call it a Cauchy sequence. And a metric space, clear that any sequence of real numbers must belong to a particular space where we can define a metric. So let us put this metric in general, and we call the metric space just X. Depending on the metric we define, we can have different types of metric space. But whatever be the metric space in which every Cauchy sequence converges, said to be complete. Another definition of the particular type of sequence is monotonic sequence. We call a sequence an is said to be monotonically increasing if an less than equals to n plus 1 for n equals to 1, 2, 3 and so on. This means that for n equals to 1, 2, 3 and so on, we will get the numbers like a1, a2, a3, and there is a fixed ordering among these numbers, like 1 is less than the next one, that is again less than or equals to the next one and so on. So if we write this clearly, we will get a1 less than equals to a2 less than equals to a3 less than equals to and so on, and this will continue. That means each number is either greater or equal to the previous number. So it is continuously increasing. So we call this sequence as monotonically increasing. Exactly similar notion, we can again define a sequence an to be monotonically decreasing if an is greater than equals to an plus 1 for n equals to 1, 2, 3 and so on. That means each number is greater than the next number, so that numbers are continuously decreasing. As an example, you can immediately see that the standard and very natural example of a sequence an equals to 1 by n. If we put n equals to 1, we get a1 is a1. If we put n equals to 2, we get a2 equals to half. If we put n equals to 3, we get a3 equals to 1/3 and so on. So clearly 1 is greater than half, which is greater than 1/3 and so on. That means a1 is greater than a2, which is greater than A3, which is greater than A4, and so on. So the sequence is monotonically decreasing. In fact, this sequence is strictly monotonically decreasing because each number is greater than the next number. Again, monotonically increasing means if we consider an as 1 minus 1 by n, for n equals to 1, 2, 3 and so on, we have for n equals to 1, the first number is 0. For n equals to 2, there is A2, the second number, which is 1 minus half, which is half. N equals to 1/3 means A3 equals to 1 minus 1 by 3, which is equals to 2 by 3 and so on. So clearly 0 is less than half, which is less than 2 by 3 and so on. So each number is greater than the previous number. So it is continuously increasing. Naturally, one can ask that what we are going to do with these monotonic sequences. Now, one thing it is clear that for a monotonically decreasing sequence, the numbers are decreasing. That means it's going down. So while it is going down, so is the number bounded or it is going towards minus infinity? A similar kind of question we can ask for increasing sequence also. So it is clear that boundedness, whether boundedness property has something to do with the convergence with respect to a monotonic sequence. We are going to discuss that. This is a very important result. A monotonic sequence an converges if and only if it is bounded. So you see, if somebody is given a sequence of real numbers and one is asked to investigate whether the sequence is convergent or not, one immediate tool one can use to check whether the sequence is monotonic or not. So if we can establish that it is a monotonic sequence, and if we just check whether the sequence is bounded or not, now checking boundedness is not a very difficult thing. So then immediately we can say that the sequence is convergent. So let us put the if part. That means assume that the sequence is bounded. But remember one thing, the sequence is monotonic. That part is always given. First, suppose that an less than equals to an plus 1, that is, the sequence is monotonically increasing. Now, since it is given if part, that means since it is given that an is bounded, we can always have the least upper bound of the sequence, we call it S. That means an is less than or equals to S for all n equals to 1, 2, 3 and so on. That means n can never exceed S. Whatever be the value of n, or n can never be greater than S. At most be equal to S but not greater than S, because the least upper bound is S. That means the sequence is bounded. Now, for every epsilon greater than 0, we can always find an integer capital N such that S minus epsilon less than an less than equals to S. That means if we can find out only one integer capital N for an arbitrary choice of epsilon, is that means a capital N belongs to S minus epsilon to S, this interval, because we can always, the function is increasing, so at some point it will exceed S minus epsilon for arbitrary epsilon. This an must be less than equals to S, otherwise S minus epsilon would be an upper bound of an. That means if we somehow claim that there does not exist such an integer, then we can treat S minus epsilon as an upper bound of an. But here we assume that S is the least upper bound. So all other upper bounds should be greater than equals to S. So S minus epsilon is not an upper bound. So for any epsilon neighborhood, we can find one value of an which belongs to S minus epsilon to S interval. Now use the fact that the sequence is monotonically increasing. That means we have already seen that a capital N belongs to S minus epsilon to S. So for every n greater than capital N, it will always imply that S minus epsilon is less than a small n less than equals to S, because let's say n equals to capital N plus 1. So a capital N plus 1 is greater than equals to a capital N, but S is the least upper bound of the sequence, so we can immediately write S epsilon less than a capital N less than a capital N plus 1 less than equals to S. And similarly, for every value of small n greater than capital N, we can always have S minus epsilon less than a small n less than equals to S. And epsilon is arbitrary but positive, fixed positive quantity, however small it might be. So we can immediately say that an converges to S. That means modulus of difference, that is an minus S, modulus of that is always less than epsilon whenever n small n greater than capital N. So capital N here plays the role of n naught. Now the only if parts show you, I will give you the outline and kind of diagram which will clear the concept, which will make the intuition very clear. We have been given that an less than equals to an plus 1, that is the sequence is monotonically increasing, and since we are interested in proving the only if part, so assume that the sequence an converges to A. Now, as soon as we say that the sequence is converging to A, we can immediately say that A minus epsilon to A plus epsilon, this interval contains infinitely many numbers, because since it is convergent, we can have modulus of an minus a less than epsilon n greater than some n naught. So here again we choose capital N, which will play the role of n naught. So n greater than equals to capital N or n naught, you can write n belongs to the interval a minus epsilon to a plus epsilon. That means we can immediately have that a capital N less than equals to a capital N plus 1, so on less than equals to a, and there would not be any number you can find in the sequence an which is greater than a. Let's see the following diagram. So here is the line, here is the a, the value of a lies here. For a fixed and fixed preassigned positive quantity epsilon, which is positive, we can always have a minus epsilon to a plus epsilon, these 2 points. Now my claim is that whenever n greater than equals to capital N, this an sequence enters the interval. That means a capital N is greater than a minus epsilon, and since it is monotonically increasing, a capital N plus 1 is greater than equals to a capital N. Similarly, a capital N plus 2 is greater than equals to a capital N plus 1, and so on. But each of the numbers must be less than a. Why? If there is such a number an which is greater than a, then an plus 1 is always greater than an. Then we can find an infinite numbers that are greater than a. And since epsilon is arbitrary, it can again exceed a plus epsilon. So if it exceeds a plus epsilon, then a cannot be the limit of the sequence a. That means we cannot say that an converges to a. So there might be a kind of contradiction. On the other hand, we can also see, if we follow the argument, then a minus epsilon to a contains only finite number of values of an. That means we have to probably look somewhere to see the converging point. But it is given that an sequence converges to a, so we cannot get any other value that exceeds a. So this is not possible. These values cannot exist. So hence the sequence is bounded because all the numbers are less than equals to a, and naturally the least upper bound is a. So this completes the proof of the fact that a monotonic sequence, monotonically increasing sequence converges provided it is bounded. Exactly similarly, we can prove the same way if it is monotonically decreasing. In this context, let us also define two very important concepts known as lower limit and upper limit of a sequence. What is the meaning of this? For every real number capital M, there exists an integer capital N such that small n greater than equals to capital N implies an greater than equals to capital M. We write that an small n goes to infinity. Similarly, for every real number n, there exists an integer capital N such that whenever small n is greater than equals to capital N, this will imply an less than equals to capital M. So previously note that it was an greater than equals to capital M, and now an is less than equals to M. So in that case we write an goes to minus infinity as n goes to infinity, because we are not putting any other restriction on an for the first and second sequence, only one side is bounded. So let us consider a set E which is a set of numbers x. Now remember, this x can be plus or minus infinity, so we take this x in the extended real number system such that ank goes to x for some subsequence ank. Now remember, we have already defined what is the meaning of subsequence. So for a particular subsequence, for some subsequence, ank goes to x as nk goes to infinity. So consider all such x values, that means all such subsequences for which we can get some x where that subsequence converges. And let's say this E contains all these subsequential limits, that means all these x values. Remember again, this x can take plus infinity or minus infinity. If we put a star as the supremum of the set A, E, and a lower star as the infimum of the set E, then the numbers a upper star and a lower star are called upper and lower limits of an respectively. So this is how we define the upper and lower limits. Now the notation used is as lim sup n goes to infinity an equals to a upper star, lim inf n goes to infinity an equals to a lower star. So this is the way we define lower and upper limits. Now naturally, since we are defining this way, each of these limits, or rather each of the numbers, each of the members of E is a limit of one particular sequence, or rather one particular subsequence that is derived from the original sequence. So naturally one question will occur that whether there is a relation between the limit of the original sequence and the limit of few subsequence or all subsequences of that original sequence n. As we see that if these limits differ, then we can define lim sup and lim with respect to the subsequential limits. So now we are going to explore whether there is a relation between the subsequential limits and the limit of the original sequence. But first, we will give some examples. Consider a sequence which contains all rational numbers. Then it can be shown that every real number is a subsequential limits. That means for every real number we can find a sequence of rational numbers, a particular sequence of rational numbers that will converge to that limit. And that sequence of rational numbers will constitute one subsequence of an. And for every real number we can find a different subsequence, and lim sup an equals to infinity and lim inf an equals to minus infinity. So this is very easy to see, and one simple example of such subsequences for which the limit is infinity or minus infinity is just a n k is n or a n k is minus n respectively. Now the second example, which is very interesting, is that we have already seen this kind of sequence where we write a n equals to minus 1 to the power n, 1 plus 1 by n. Now you see, as n goes to infinity, this 1 by n goes to 0, and as if n takes even, depending on whether n is even or odd, minus 1 to the power n becomes 1 or minus 1. So lim sup of n equals to 1 and lim inf of n equals to minus 1. That means if we consider a subsequence which consists of only the odd, which corresponds only to the odd numbers of n, then that will converge to minus 1. And if we consider a subsequence that corresponds to only the set of even integers, then the lim sup would be 1. The third sequence is that this is a result, I can say, that limit n equals to a as n goes to infinity. This will happen if and only if lim sup n equals to lim inf n equals to a. The proof would be very simple, but intuitively it is clear, because if we see that there is a subsequence and we can define, there are several subsequences and we can define that lim sup would be an, that is the upper limit is a, and lim inf of an, that is lower limit of an, is same as a. That means it is intuitively clear that probably all the subsequences are going towards a, because if there is a difference, then we will have a change in the lim sup and lim in values, but since the values are identical, then all the subsequences will go to a, and hence the original sequence should go to a. On the other hand, if the original sequence goes to a, we can think that whatever be the subsequence, this should go to a. That means the lim sup and lim in must be equals to a. So intuitively this is very clear, and very simple mathematical arguments can give you the formal mathematical proof, which I leave it as an exercise. Now I will just consider three sequences and investigate their convergences. So first one is for p greater than 0, let us consider the sequence 1 by n to the power p, and we will prove that limit n goes to infinity 1 by n to the power p is 0. The proof is extremely simple, because if we consider, because as n goes to infinity, it is clear that denominator gets larger and larger. So if we consider 1 by n to the power p minus 0, absolute difference of that means modulus of 1 by n to the power p is less than epsilon, we can immediately see that whenever n exceeds 1 by epsilon to the power 1 by p, which is indeed a very, very large number, because epsilon is small, so 1 by epsilon is very large. So this, whenever n is greater than this 1 by epsilon whole to the power 1 by p, then we will always have 1 by n to the power p minus 0 mod of that less than epsilon, and hence we can immediately write that the limit of 1 by n to the power p equals to 0 as n goes to infinity. The second sequence is very important. We say that limit n goes to infinity p to the power 1 by n equals to 1 for p greater than 0. Now let us prove this thing. First consider p greater than 1. So when p is greater than 1, and put xn equals to p to the power 1 by n minus 1. Since p is greater than 1, clearly xn is greater than 0. Now using binomial theorem, what is p? P is 1 plus x whole to the power n. Now use binomial theorem. So p equals to 1 plus x to the power n, and keep this expansion only up to second term. So this must be greater than 1 plus n into xn, because each of the terms is positive, because xn is positive. So this 1 plus xn to the power n is greater than equals to 1 plus n xn. This immediately implies that xn is less than p minus 1 by n, or at the same time xn is bounded below by 0. So 0 less than xn less than p minus 1 by n. And n goes to infinity, the right side goes to 0, so xn goes to 0 as n goes to infinity. If we put p equals to 1, then this p to the power 1 by n is always equals to 1, and hence its limit is always equals to 1. Now for p less than 1, proof follows by the same argument as p greater than 1, but only we have to take the reciprocal of that. So the next and the last sequence that we are going to consider today is n to the power 1 by n, and we will show that limit n goes to infinity, n to the power 1 by n equals to 1 as n goes to infinity. So again, put xn equals to n to the power 1 by n minus 1. It is clear that for any value of n, if we put n equals to 1, then 1 to the power 1 is 1. If we put n equals to 2, then n to the power half or 2 to the power half is at least greater than 1. So for every value of n, n to the power 1 by n is greater than 1, and hence xn, which is equals to n to the power 1 by n minus 1, is greater than 0. So again, we use the same kind of argument. We take n equals to 1 plus x to the power n, and using binomial theorem and returning only one term, we have n equals to 1 plus xn to the power n greater than equals to n into n minus 1 by 2 into xn square. A simple manipulation will give us xn less than equals to square root of 2 by n minus 1, and obviously xn is positive. Just note one important point is that xn less than equals to square root of 2 by n minus 1, and we assume that n is greater than equals to 2, because it's a sequence and it's an infinite sequence, so n can always be greater than equals to 2. As n goes to infinity, square root of 2 by n minus 1 goes to 0, and hence xn goes to 0 as n goes to infinity. So we have considered three different sequences, and we have seen the convergence behavior of these sequences. Now these sequences are very important, and we should try to remember the limits of this sequence, but if not, it's not a big issue. We can prove just by one or two lines. So today we have learned few more important properties and results about sequence of real numbers. One important sequence is Cauchy sequence, and we have seen how convergence is related to Cauchy sequence. Again, we have also learned one important type of sequence which we call monotonic sequence. That means a sequence might be monotonically increasing, or a sequence might be monotonically decreasing also. There might be some other sequence which are not monotonic, but if we have somehow, if we see a monotonic sequence, we can immediately have some idea about its convergence. Okay, and we have related this convergence of monotonic sequence with another property which is called boundedness. So we have seen one or two results relating to that. At the end, we have discussed few extremely important, very special type of sequences, which are very interesting. It is not very easy to see what would be the converging point or the value for these sequences, but we have proved the convergence or converging behavior or the asymptotic behavior of these sequences. So this together gives a brief idea about how one can work with a sequence of real numbers. We will extend later on this same concept, same kind of concept when we deal with improbability theory, when we deal with sequence of random variables.